This is our video 5 on heat, and this video is going to be on thermal energy or heat transfer. So heat can be transferred from hotter objects to colder objects, and it can travel from one place to another in 3 different ways. So one is conduction, the other one is convection, and the last one is radiation. Both conduction and convection require matter to transfer the heat. So you have to have the matter, the stuff, to travel through for the heat. If there is temperature difference between two systems, heat will always find the ways to transfer from higher to lower system. So conduction happens when the transfer of heat between substances that are in direct contact with each other. And the better the conductor, the more rapidly the heat will be transferred. Metal is a good conductor of heat. So conduction occurs when a substance is heated, and particles will gain more energy and vibrate more. And these molecules then bump into nearby particles or molecules and transfer some of their own energy to the neighboring particles. This then continues and passes the energy from the hot end down to the cold end of the substance. So another one that I mentioned is the convection. And convection occurs when warmer areas of a liquid or gas rise to cooler areas in the liquid or gas. So cooler liquid or gas then takes the place of the warmer areas and which have risen higher. So it's like replacement one of the other. And this results in a continuous circulation pattern. Water boiling in the pan is a good example of these convection currents. Another good example of convection currents would be the atmosphere. And even the Earth's surface is warmed by the sun. The warm air rises and cool air moves in. And the ocean currents as well. They're warmer and colder currents that will represent the convection. So another one is radiation, and radiation is the method of heat transfer that does not rely upon any contact between the heat surface or source and the heated object, as it in this case, like conduction and convection, they need the objects to be in contact. So the heat can be transmitted through empty space in radiation, and it's also called infrared radiation. This is the type of electromagnetic radiation as well. So no mass is exchanged and no medium is required in the process of radiation. Example of radiation is the heat from the sun or heat released from the filament of a light bulb. So thermal conduction can be viewed as an exchange of kinetic energy between colliding molecules or electrons. And the rate of thermal energy transferred by the conduction through a slab of area like A and thickness L can be represented by the formula that you see right here. So heat over time is equal to, and then you have the fraction, and then you have A for cross-sectional area of the slab, and then the change of the temperature between the cold and the hot. It can be like the house. On one side of the house it's hot, and the side of the house it's cold, or vice versa. And then divided by, you have L over K. So L is the thickness of the slab, the insulation area, and K is the thermal conductivity of the material making up the slab. So the larger K means better heat flow. So let's look at this example. If it is 22 degrees Celsius inside and 0 degrees Celsius outside, what is the heat flow through a glass window of area 0.3 meters squared and thickness of 0.5 centimeters? The thermal conductivity of glass is about 1 watt per meter squared Kelvin. So the formula that we looked at, the heat flow, so we have heat per time is equal to, and then we have diffraction, and at the bottom we have the sum of all the thickness of the insulating material over the K, the thermal conductivity. And then on the top we had the area and change of the temperature, or the difference between the temperatures. So here we have K is 1 watt per meter Kelvin. So L, the thickness, is given 5.5 centimeters. So that's 10 to the negative 2. All of it divided by K, and K is 1 watt. So that's just 1 watt per meter squared Kelvin. So I use these two variables, and then I have the area, and the area is we have 0.3 meters squared, so 0.3, and the change of the temperature, or the difference of the temperature, and that is 22, because it went between the difference between 22 and 0 degrees outside. So I have the heat flow over time is equal to 1320 watt per second. And if you just calculated the heat flow, that would be again 1320 watts. In this second example, they say how much heat is lost per second through a double pane version of that window, the problem that we just did, with 0.5 meter air gap. The thermal conductivity of air is given to be 0.3 watt per meter squared Kelvin. So I can use the same formula, and I have the same area, 0.3, and the temperature difference is still the same, 22. I can say Kelvin or Celsius, it doesn't matter, and because the difference would be the same. And then the distance between them is 0.5 centimeters, so that's 5 10 to the negative 3, so the distance between the glasses. And then the air conductivity is 0.03. So if I calculate how much heat per second is lost through conductivity through the air, I will get 39.6 watts per second. In this question, they say a wall on a house is 20 centimeters thick and is composed of wood and a non-insulator. Given that the house temperature is 15 degrees Celsius, insulator thickness is 12 centimeters, wood thickness is 8 centimeters, and total cross-sectional area is 15 meters squared, concrete, and they give you 33 joules per second heat flow rate, determine the total thermal conductivity K of an insulator if the indoor temperature is kept at 22 degrees Celsius. And they give you the thermal conductivity of wood, 0.11 joules per second, meters and degrees Celsius. So we have the formula heat per time flow is equal to, again, the area, the difference in temperatures, and then the sum of all the lengths of the insulators over their thermal conductivity. So there's many different ones, and over thermal conductivity. So the area is given 15 meters squared, and the difference in temperature is 22 and 15. And then I have all the thicknesses. So the first one is wood, and it is 8 centimeters thick, so 0.08. And the thermal conductivity of wood is 0.11. Then the unknown insulator is 12 centimeters, so that's 0.12. And we do not know its thermal conductivity. That's the one that we have to find. And all of that is equal to the heat flow rate, which is given 33 joules per second. So now from here I can solve for K. So far I simplified the my big fraction. So I simplified this part into this. And then I times the numerator and the denominator by K. So I multiplied this side by K and this whole thing by K. So when I distribute it, I got my K on the top and I have K over here. So now I can cross multiply my fraction, and this is what I'm going to get. So this is my next expression. So I'm going to subtract 2376 from both sides, and I will get 8124K is equal to 396. So K is equal to 0.049 joules per second meter degrees Celsius. I found this question in Monterey Institute of Technology. I always suggest for my students to watch this, and it is under temperature and heat lesson. They have a few good questions always at the end of each of their lessons, and if you can solve those questions, you should be able to solve any AP exam question. So it is on my webpage, the suggestion to use Monterey Institute of Technology AP Physics lessons. In this question, they say an Arctic explorer built a wooden shelter out of wooden planks that are 1 centimeter thick. To improve the insulation, he covers the shelter with a layer of ice of 3.2 centimeters thick. Compute the R factor for the wooden planks and the ice, and R factor is going to be that the length or the thickness of it over the thermal conductivity. So they call it R factor. And if the temperature outside the shelter is negative 20 degrees Celsius and the temperature inside is 5 degrees Celsius, find the rate of energy lost through one of the walls if the wall has dimensions of 2 meter by 2 meters, so 4 meter squared area. Find the temperature in the interface between the wood and the ice. So the first one I have to find is the R factor, and the R factor is equal to L over K. So in this formula, Q over T is equal to the area and then the change of the temperatures. And then you have the sum of all the L's over K. So L over K is called the R factor. And so for the wood, we have, so I'm going to call 1 for the wood. And that one is called, the thickness of it is 0.01, it's 1 centimeter, divided by 0.11, I believe they said. K for wood is 0.11, so that's 0.11. And that gives me the R of wood equals to 0.091 and measured in meters squared seconds degrees Celsius per joule. I can do the same R factor formula for the ice. So for the ice, I have the thickness of the ice is 0.032, so it's 3.2 centimeters, and they give you the thermal conductivity of the ice, which is 1.6, and that will give me 0.02 meters squared seconds degrees Celsius over joule. And then for the next question, for B, they ask you if the temperature of the shelter is outside of the shelter is -20 and inside is 5, find the rate of the energy loss. So for the second part, if I'm looking for the rate of the energy loss, I have Q over T is equal to, the area is equal to 4 meters squared, so that's 4. And then the change in the temperature is 25 degrees, so that's 5 minus -20. And then divided by 2 R factors, and I found one to be 0.091, and the other one is 0.02. And that will give me 901 and measured in joules per second, or 901 watts, because the measure joules per second is watts, the same as power, it's energy per second. I cleared the board a little bit, and so now I have to find the temperature at the interface between the wood and the ice. And I'm gonna use this equation, applying it for the wood only. So I will get the heat flow, the one that I just found. So I have the heat flow is equal to the area, the temperature between the inside minus the temperature between the wood and the ice, and then, or wood and ice, and then divided by L over K for wood only. So that will give me 4 is the area, meters squared, and then the temperature is 5 minus the temperature I'm looking for, and then all of it divided by the R factor for the wood, which is 0.091, and all of that is equal to the one that I just found, 901. So T is going to be equal to -15.5 degrees Celsius. So that's the temperature between the wood and the ice. So Stefan Boltzmann's law, sometimes called Stefan's law, related to temperature of a black body to the amount of the power it emits per unit area, and the law states that the total energy emitted or radiated per unit surface area of a black body across all wavelengths per unit time is directly proportional to the fourth power of the black body's thermodynamic temperature. So in other words, you have the proportionality factor, and then you have the temperature to the fourth power. So this law that expresses the total power per unit surface area, or in other words, sometimes called the intensity, that is radiated by an object often taken to be a black body. So this law is used, the Stefan Boltzmann's law is used to explain how much power the sun gives off, knowing its temperature. And also this law is predicting how much heat the Earth radiates into space. And when we say black body, we mean this is an object that absorbs all the electromagnetic radiation or light. And so the electromagnetic radiation includes the whole spectrum of the waves that the sun produces. And so it's from the longer wavelength, which is radio waves, then microwave have shorter wavelengths, and then infrared, invisible, ultraviolet, X-ray, and the gamma rays. Gamma rays have the shortest wavelength and the highest frequency, and the radio waves have the longest wavelengths and the lower frequency. So the black body radiation absorbs all electromagnetic radiation or light that strikes it. And to stay in thermal equilibrium, the black body also must emit radiation at the same rate as it absorbs it, so the black body also radiates well. And actually, any matter that has a temperature higher than its surroundings emits radiation at various frequencies. And many astronomical bodies, such as stars, can be considered to be almost perfect black bodies, so we can apply all the characteristics of the black body to them. And colder objects emit wavelengths with very low frequencies, and hotter objects emit the wavelengths with the higher frequencies. So the black body radiation is a term used to describe the relationship between the object's temperature and the wavelength of electromagnetic radiation it emits. A black body is an idealized object that absorbs all electromagnetic radiation and comes contact with it, and it then emits thermal radiation and is continuous. It's in a continuous spectrum according to its temperature. So the energy production of the stars happens at its core and is very energetic radiation. So the core is surrounded by thick layers of gas. This will absorb the radiation produced in the core and eventually re-emit it at heat radiation. So we luckily cannot see the radiation produced during the fusion. It is much too energetic and would kill us if it could escape at the moment when it was produced. So it takes thousands of years before the heat produced at the core of the star is finally emitted as heat radiation. Another word for heat radiation is the black body radiation. And this is why they say that the stars are almost like black body radiation, has black body radiation, because they don't emit the energy that they have right away. It takes years and years before the energy that they produced actually comes out. Only a small amount of stars' light will be produced by magnetic effects above the star surface. So solar flares and similar events will emit light in the same way as some gas lamps make light. So this is not black body radiation, but it is only a fraction of the total produced light. So a small fraction of stars' heat radiation will be absorbed, and exact absorption tells us what stars are made of. And this is when we use spectroscopy to determine what stars are made, what type of gases are in the star, because of their absorption spectrum. So in reality, stars only approximate a black body, and when looking in details, it gets a really complicated concept to explain. So here in this formula, you see the sigma sign, that is Stefan Boltzmann constant 5.710 to the negative 8, and then you have area, and then you have E is the constant between 0 and 1, and called the emissivity of the object. And because the black body object has emissivity close to 1 perfect emitter, so 0 means no emitting energy, and black bodies emit all of its energy, so that means E is equal to 1. And T is the object's Kelvin temperature, because there's no delta, so I have to use temperature in T. And another object is the white body, is one with a rough surface that reflects all incident rays completely and uniformly in all directions. The graph you see in this picture is a model based on the concept of emissivity and thermal radiation from a body, or solid, liquid, or gas, at any temperature above 0 Kelvin. The emissivity at a specific wavelength is the ratio of the amount of energy emitted by the body to the amount of energy emitted by a black body at the same temperature. So emissivity is often symbolized like E, the one that you see in the the formula above, and you see it in the next formula right here. And so it's the Greek lowercase epsilon letter, and then emissivities range from 0, no emissivity, to 1, which is black body radiation. And so the graph represents how the radiation happens at different wavelengths. So the hotter objects have shorter wavelengths, and the cooler objects have longer wavelengths and lower frequency. So let's look at some questions and try to use these formulas. I haven't seen many questions related to this topic on AP exam, and I have a lot of videos related to this topic, conceptual videos for you in our lectures online. So I'm just going to look at some questions and try to solve them with you to help you to use the formulas and be familiar with them. So in this question, they say, suppose you baked a cookie. When you pulled it out of the oven, it was 200 degrees Celsius, and you would like it to cool down to 20 degrees Celsius before you eat it. If the cooling process involves only radiation and a cookie has an area of 50 centimeters squared and its emissivity is 0.1, what is the rate of radiation the cookie creates while it is cooling down? So let's use the formula that we just saw. So I have the heat flow over the time is equal to the Boltzmann constant, the area, the emissivity, and then I have the final temperature to the fourth minus the initial temperature to the fourth. Plugging in the numbers, I have the Boltzmann constant 5.7 10 to the negative 8 times the area, which is 50 centimeters squared. Centi squared is negative 4. Emissivity is 0.1. And then the temperatures, I have to convert it in Kelvin. So the final temperature is 20 degrees Celsius. That's plus 273. That's 293 to the fourth power. Minus initial, which is 200, plus 273 gives me 473 degrees Kelvin, or Kelvin. And so now if I do my calculations, I'm going to get negative 1.22 watts, or joules per second. And this is the rate at which the cookie is losing its energy, 1.22 joules per second. So the questions that are related to these type of formulas are direct, so you just plug in the numbers and you do your calculations. Most important is to understand the concept of it, and I try to explain the best I can, but I would suggest that you watch the videos in our lessons about the black body radiation and Stefan Boltzmann's law of radiation. And I think this will conclude our 5th video on heat, where we covered thermal energy and the heat flow, transfer and flow. And I will thank you for watching this video, and I'll see you in the next one.